your screen also. So we are live on YouTube now. So good evening to everyone, to all the viewers. This is Saurabh Kaushal, Director, Smartcircuits Innovation Private Limited from India. And today we have two very, the great speakers are with us. One is Mr. George Salazar from Johnson Space Center, NASA, United States of America. And he's also served as a mentor to Smart Circuits Innovation Private Limited. So welcome, George sir, on this live interactive session. And today, along with me, we have Dr. Paramjit Singh sir, who is the principal of Army Public School, Ambala, Kent, who will moderate this session along with me. So welcome, Dr. Paramjit Singh sir, who is also doing a lot of great work in his school in the field of innovation as well as in the field of space technology. So we have Dr. Paramjit Singh sir with us today. So welcome to both of you on this live interactive session. And today, Mr. Joe Salazar is going to discuss about the technical challenges in the human space flight, as our own space agency is also looking forward for launching a human space mission in the coming years. So it would be a great session where George Salazar sir will tell us more about the technical challenges. What all are the technical challenges in the area of human space flight? So now I request Dr. Paramjit Singh sir to please welcome Mr. George Salazar sir.
Thank you, Saurabh. Thank you for the welcome. Good evening, everyone in India, and good morning, everyone in USA who are watching us live. And it's my proud privilege to welcome our esteemed speaker of the session, respected Mr. George Salazar, who has received his Bachelor's of Science in Electrical Engineering from the University of Hudson and his Master's of Science in Systems Engineering from Southern Methodist University. Mr. George has over 30 years of experience in telemetry, communications, speech control, command and data handling, audio, displays and controls, intelligent lighting, project management, and system engineering. He has been involved with the design of advanced telemetry, voice recognition, and intelligent systems, of which he has received various invention patents. His various systems were an important part of the Space Shuttle and Space Station program. He is currently serving at NASA's Johnson Space Center as the Human-Computer Interface Technical Discipline Lead to develop advanced human-computer systems. He is also working with astronauts as they learn to use these systems. His work is helping to take us into the future of space exploration. And I am sure that today's session will be a great session for everyone who is watching us live. And I'm sure that with his vast experience in this field, he is going to motivate many more astronauts as well as scientists in the field of space. Welcome, Mr. George. Over to you.
Thank you for having me.
It's my pleasure. Over to you, Mr. George.
Thank you. All right. So, can you see the presentation?
Yes, sir.
Yes, sir.
Okay, very good. All right. So thank you for having me. Thank you for inviting me. And good morning, good afternoon. I guess wherever everybody's at these days, it's morning here. So what I want to do is just kind of give a high-level presentation to give you a feel of what it takes to do human spaceflight, especially in future space missions. And so what I'm going to do is share with you some of the topics. Now, you notice the background there is Star Trek. I grew up watching Star Trek. And what's interesting about that background is a few things that you can that I'd like to note about it. First of all, this is the future, all right? And secondly, the crew is it's international and even federation, if you will. You got a Vulcan, you got people from Russia, you got people from the Philippines, Scotland, Africa, and so that's really what's the reality of future missions is that it's going to take all of us involved. Even obviously India is going to be involved with some of this exploration because the United States cannot do it alone, and that's why we did Space Station with 14 different nations. So that's a representation. And also, if you look at the Star Trek Enterprise, that's a futuristic ship, and we're going to need something like that for our future missions. So, with that said, I want to just again talk a brief history of human spaceflight. Then I'm going to talk about current and planned human spaceflight programs, and then the key technology challenges. And I'm going to touch on some of the more challenging ones. That we have a whole bunch, but I just want to share with you and give you a flavor of some of the technology challenges that we have, and then some concluding remarks. So let's talk first about the brief history of human spaceflight. And so let's start with the Mercury program. Mercury program was the first human spaceflight mission. We didn't know anything about how humans are going to behave in space. We had sent mammals into space. Lakita was the first mammal in space, and the Russians sent that dog up, trying to understand, can mammals live in space? And then Yuri Gagarin was the first astronaut that went there. But for the United States, the Mercury program was kind of an answer to the Soviet space program at that time. And so the Mercury, and there you see a picture of the 7 astronauts. These were all military astronauts, and one of the reasons that were chosen as military folks was because they were high-risk people. They accepted risk. They understood there was a lot of risk in the space program. Like I think it was Alan Shepard said something about you're sitting on a capsule on top of a highly explosive rocket right under your seat. And so it was very challenging, but we need to understand, could humans operate and live and work in space? And so we accomplished that, and we understood we could live and work and eat in space. Then the Gemini program came about. And so Gemini, it was a bigger capsule. It housed 2 astronauts versus 1 astronaut on Mercury. And we needed to know and understand how humans can behave for more than a week in space. In fact, Gemini had 2-week missions. And also, more importantly, was rendezvous and docking, because that was going to be the critical part for the Apollo space program, because we're going to have to launch 2 separate vehicles and then dock them together, and then go off to the moon, and then land on the moon, come back up from the moon, dock together, and
I think there is some issue with the audio, so we'll check the technical issue. We'll get back to you in a while. So let me check with the George, sir.
Hello?
We are,
Are you
you're
there?
audible, Mr. George. You're audible now.
Okay. All right. So can you see it now?
No, we cannot see your screen at present.
All right. All right. Stand by. Let's see. Apparently, I got disconnected. I just saw a note here. All right. Hopefully, you can see
Yeah,
it now.
yeah. Yes, yes, sir. Please go ahead. Yeah.
Okay. All right. Sorry about that, but let's see. I'm not sure exactly where I lost you guys, but so I talked about the Mercury program, and basically, in short, it was a way of learning how to live and work in space, and also because humans live and work in space. And then the Gemini program went a step further, and and we needed to understand if we could rendezvous and dock with two separate spacecrafts going at 17,005 miles an hour. And that was going to be critical. That was going to be absolutely critical for the Apollo space program, because the Apollo space program called for the rendezvous and docking of spacecrafts as a way of, not only saving costs, but also a more simplistic way and safe way of landing humans on the moon. And then the Apollo space program came about afterwards. And so there you see the launch of the Saturn V rocket, one of the most powerful rockets ever developed by Wernher von Braun. And we learned to live and work on another planet for the first time. There's I think that's Gene Cernan hopping on the moon surface, and then right below that is the lunar service module getting ready to land on the moon. One of the interesting things about the lunar service module was the fact that there was a bit of automation and autonomy. It was supposed to land automatically on the moon, but Neil Armstrong, and you probably know the story, saw that it was going to land on a rocky area, and if that would have occurred, they would have crashed. So Neil Armstrong turned off the autonomous system and took over manually, and because Neil Armstrong was one heck of a pilot and very calm and collective, he was able to land the Eagle on the moon safely. And then we had the Space Shuttle program. Space Shuttle program was a program of the first reusable spacecraft. Interesting thing about the Space Shuttle is that it operated kind of like in three phases. It could launch like a rocket, it could orbit like a satellite, but it also re-entered the Earth's atmosphere as a landing jet aircraft, if you will. Of course, one of the big challenges for the shuttle program was the operations costs because of the complexity of the vehicle. It took a lot of people to service it. They envisioned 25 people in a little jet hangar trying to service the space shuttle. In reality, it was a huge, complex orbital processing facility that required thousands of people to maintain and operate the space shuttle and get it ready for the next flight. So, going on, let's now talk about the current and planned human spaceflight programs. And starting with this picture here is the phased approach to Mars. And so, what you're seeing here is the Earth, obviously the Moon, and then the Mars. And so each one of these has a job to do in order for us to get to Mars. So Earth, we're right here now with Space Station. I'll say a few words about Space Station in a little bit, but we're Earth dependent right now. We call it Earth dependent because Station is not too far away from Earth. It's only a quarter second in communications delay. But once we start going to the moon, things are going to change a little bit. Returning back to the moon, we've been there, but it's been a long time, 51 years plus. And so there's a lot of activity that's going to go on the moon because that's going to be what we call our proving ground. It's proving ground because it's going to teach us about what technology works, what doesn't work, and for how long. We need to understand that, get a good handle of it, because once we are ready to go to the Mars, all that stuff, all that technology that has been developed for Moon and basically learn about it is going to take us to Mars. Mars is going to become Earth independent. And the reason for that is because of that long distance from Mars to Earth. In an emergency situation, it's not a matter of like you're on the moon, you can come back in 2 or 3 days. In an emergency situation, we're talking months, for sending an emergency return vehicle or sending from Mars back to Earth a emergency vehicle that has a ill crew member. So let's talk now about the space station. All right, so space station, that's right now orbiting the Earth. And the interesting thing about space station, it's a very great microgravity environment. Notice that I didn't say zero gravity, because there's no such thing as zero gravity. Everything basically pulls on everything else if it's mass. And so it's an opportunity to conduct unique science experiments and learn quite a bit about living and operating living and working rather in a microgravity environment. One of the things about the microgravity environment is that there's a phenomena that occurs because of the microgravity environment that basically does not happen on Earth, and that's because of the microgravity. And so now you can, in space, see the hidden effects due to gravitation, due to the 1G gravity environment that we live in. And so you're able to do things like, you learn about the absence of buoyancy and sedimentation. Things in space, basically float. But of course on Earth they're falling to, they want to fall to the center of the Earth as the theory goes about the pull of gravity. And then you got the absence of convection. Here on Earth, heat travels upward, in a convection fashion because of the 1G environment. In space, there is no convection. And so that's an opportunity to learn about things, for example, fire in space and other phenomena that you cannot see that on Earth, but you can see in the microgravity environment. There's an absence of hydrostatic pressure. On Earth, if you go deeper into the sea, the pressure gets worse and worse. I know as a scuba diver, every 33 feet going down into the water, the atmospheric pressure increases by 14.7 pounds per square inch, or 1 atmosphere. But you don't have that in space. So it's another opportunity to do experiments and observe what happens in a microgravity environment. And then the other thing is containerless float. On Earth, you got water in a bowl, okay? So you can see the water in the bowl, and it's all around the bowl. In the microgravity environment, interesting enough, water becomes a sphere, and it's no longer touching the walls of the bowl. And so that's an interesting phenomena. There you see a picture of Scott Kelly that spent over a year in space, what looks like a little play ball, but it's not. It's actually a liquid with painting on it that kind of looks like the Earth. But that's all liquid. On Earth, that thing would have fallen to the ground and splashed like water. And there's also conducting technology experiments. What you're seeing there is a robotics refueling mission demonstration that was done on station. And the importance of this is for long duration missions because it's the ability to store for a long period of time cryogenic fluids. Cryogenic being very, very cold in a microgravity environment. We need this because cryogenic fluids are important for fuel, and they're important for coolant, such as life support systems that provide oxygen for the astronauts. But nothing's perfect, And so some of these containers could leak. And so we have to understand how to build good containers where they don't leak, and basically would render a failed mission because we've lost all our fuel or we've lost coolant to provide environmental life support systems for the astronauts. And of course, interesting enough, the technology of toilets. You might not think it's a big deal on Earth, but it's a big deal in space. There's a lot of challenges of doing a good designing a good toilet, and they're upgrading the space station toilet right now. There you see a picture of an astronaut servicing the toilet on space station. On shuttle, it used to break down frequently. It was just a challenge dealing with let's call it toilet technology, for the lack of a better term, in the space environment. But it's important, you want a good working toilet, for the astronauts, because it's frustrating, as I've heard them say, when the toilet's not working properly. And of course, as I mentioned previously about Scott Kelly, he spent 360 something days in space, and to learn about what the effects are of long durations in space for the human body. Scott Kelly suffered a lot of physical issues, blood pressure problems, headaches, eyesight problems. There were a lot of things that he got affected because of the space environment, and not to mention, the bone, the calcium decline in his bone structure. And the reason for the calcium decline is because of the lack of a microgravity. Here on Earth, our bone structure is designed to produce calcium to strengthen our bones so that we can stand up to the 1G environment or the gravitational pull. In space, when there's no gravity pull per se, because they're free falling around the Earth, the body says, hey, I don't have to produce calcium because I don't feel the effects of the forces of gravity. So those are some of the challenges going into future deep space missions. Scott only spent 1 year in space, roughly, but going to Mars is going to be 3 years. So he only did about 1/3 of what it takes to for astronauts, to go to Mars and come back. So there's still some challenges there. So here is the Artemis program, the latest program that NASA is undertaking, and it's a program, it's the proving ground of going back to the moon and living and learning, operating in the moon environment. And so the first thing is the first human spacecraft on the moon in the 21st century. That's going to be Artemis 1. It's not going to have any humans in there, but it's going to demonstrate and prove out the technology, especially the heat shields when they're coming back to the Earth at a very high rate of speed through the Earth's atmosphere. And then Artemis 2 is going to be the first humans to orbit the moon in the 21st century. And then we're going to look at some high-powered technology for propulsion systems. I'll say more about this later. But we need to understand and develop high-energy propulsion systems that can take us to Mars very quickly and even beyond Mars. And, of course, we're going to have the first pressurized module delivered to Gateway. Gateway is going to be like the space station, but only for the moon. And then we're going to have a human landing system delivered to the Gateway. And, of course, and then we're going to have a crewed mission to Gateway and then to the lunar surface. On the lunar surface, we're going to have commercial partners. And maybe here's an opportunity for India to get involved in commercial lunar payload services, for delivering things like large cargo landers, robotics, communication systems, and then, of course, habitat systems, which are going to be obviously very critical for the astronauts because they're going to be living there a long time. Apollo program, if you combine all the Apollo space programs that landed humans on the moon, about 12 astronauts, but we only spend, maybe about 13 days total altogether with all those missions. And now we're talking about spending months on the surface of the moon. So it's a dramatic difference compared to the Apollo space program. And of course, they're going to have to be doing a lot of extra vehicle activities, whether you know this or not, but extra vehicle activities are very, very dangerous. And they try to avoid extra vehicle activities as much as possible. Those spacesuits, actually a spacesuit is the smallest spacecraft ever built, because it fits one person. It's got life support systems. It's got communication systems. And it's got, to some extent, it's got waste management systems in there. And so it's a very mini spacecraft, but it's very thin, and it cannot handle if it was to be hit by a high energy meteorite. So we're trying to avoid extra vehicle activities as much as possible. So the challenge is maybe doing a lot of things robotically as much as possible, and the astronauts not having to go outside as often as we hope. We don't want them to do. So let's talk about deep space mission operations. This is to give you an idea of how many people support deep space missions. Okay, so right now we got the orbiting space station. That's our current space station in there. I think right now we have 5 astronauts. 2 of the astronauts are going to be coming back on Demo 2 on August 2nd. I'm going to be supporting that mission because that's one of my responsibilities is the SpaceX demo systems. And so we got mission control that you probably see on television, and there's about maybe 50 to 75 people in that mission control center. But those are flight controllers, and these are the people that are looking at a lot of data on the system. But sometimes they don't understand things, and they call upon the mission evaluation room people. And these are all engineers, systems engineers that understand the systems inside and out, and so they support the flight controllers. And also we have the folks in Moscow that are also supporting space station. So collectively, we have quite a few people supporting space station. And one of the reasons is because it's a huge spacecraft, one of the biggest ever built, especially in the space environment. There's over 350,000 sensors and over 100 computers that have to be monitored 24 hours, 7 days a week. And they look at the range of complexity. If you look at something like this, is what's going to be needed for Mars in terms of complexity of sensors and intelligent systems with computers and all that. And of course, the other aspect of this is seeing if spacecraft systems can last for a long period of time. And of course, the space station has been orbiting now for over 20 years. And so it gives us a feel for how well structures can behave and last in the space environment for a long period of time. And now let's talk about the future, the notional. Okay, so there's a picture of the gateway habitat to the left, and then to the right, we have what's called the Mars transport, which basically would launch from the moon to Mars. But there's something big, there's going to be a big difference is that for the most part, you're still going to have mission support because it's only a quarter of a second, 1.2 second delay roughly in communication. So it's not a big deal. And so you still have people monitoring a lot of the systems on Gateway, on the moon, and what have you. But as we start going to Mars, the delays start getting worse and worse, and we're going to have to now depend on what we call onboard mission control. Let's call it, for the lack of a better term, onboard artificial intelligence that provides the ears and eyes of representing the flight controllers on the spacecraft itself. And so we're going from a crew mission control dependent environment to a crew vehicle dependent. This is, and that's why the reason the Mars expedition is called Earth independent, is because we're going to be so far out that we're going to have to depend on the systems for keeping the crew alive, for keeping the vehicle healthy. And so, but there's a lot of challenges ahead. And let's just talk about the human. The technology is going to have to be there to ensure that the astronauts' both physical and psychological health are maintained. We got to produce water. We cannot take all the water for a 3-year trip to Mars. We're going to have to learn how to produce water on Mars, and we learned that by experimenting on the moon. obviously, we got to have air to breathe. That's going to be critical. So we got to develop environmental life support systems that do the job of producing oxygen and reliably, maybe close to 100% reliability. Food, they can't take all the food for 3 years, if we're going to Mars. So we're going to have to learn how to grow food on another planet. Obviously, we're going to have sunshine, to keep our circadian rhythms in order, for sleeping, and for being awake. One of the challenges of going to Mars is that the Earth's radiated energy decreases by 1/r squared. So that's going to be a challenge too for humans on Mars. And as we start going further into space, we're going to have to develop artificial light that kind of simulates, if you will, sunshine to keep our circadian rhythms in order. And of course, exercise, because of the gravity changes, and our bodies are still accustomed to the 1G environment. Working with a crew, you're going to have an international crew. I've talked about the Starship, the Star Trek Enterprise having an international crew, and even a Federation crew. And same thing with going to Mars. We're going to have international partners there, and the international partners, obviously have a different culture, different belief system, but collectively they have to learn and live and learn and operate collectively as one team, to accomplish the mission. So it's not advertised, but working in a team can be challenging. So that's another area that we have to be monitoring too, as well as team interaction. And isolation, they're going to be far away from loved ones. And I think many of you can attest that if you've been away from, mom and dad, or, your grandparents or your wife or spouse for a long period of time, you start missing them. So imagine that you are on another planet and you see Earth about the size of a little marble, how that can affect you. We still don't know how we are going to behave as humans being that far away from Earth. So we need systems to help monitor that and keep us healthy from a psychological standpoint, as well as physical standpoint. And of course, habitat. You don't think much about a habitat, but you don't want to live in a cramped quarters. Imagine living with, let's say, if you got two brothers and two sisters in a room that's very, very small. They start getting on each other's nerves, and so you have to have a habitat large enough, to give people their own personal space. But at the same time, you have to watch the weight. You have to watch not only the weight of this vehicle, because this vehicle is going to have to be transported to another planet, but you also have to think about the power, because power is very important in spacecrafts. And of course, you got the radiation environment too that can affect the astronauts. And I'll say a little more about that later in the presentation. So let's now kind of briefly talk about key technology challenges. And again, this is high level, and some of the ones that are important, but very challenging to develop. And the first one is propulsion to Mars. Get the crew there as quickly as possible for radiation exposure. The less time they're spending in space, the less radiation that occurs. And you just can't launch from Earth to Mars in a straight line because of the effect of the orbital mechanics of it would make it an inefficient orbit. So here you see Earth and Mars very close together, but if you launch at that point, it's going to have to go around the sun. So it's a very inefficient trajectory, as opposed to kind of doing what I call the dog chasing the cat. Here's the cat and here's the dog going in this direction, to catch up with the cat. So understanding that is important. The launch window is important too. If you miss the launch window, it takes a lot of more energy to try to get to Mars. And so the technology of propulsion to Mars is going to be very, very important. Spacecraft weight and power is very important. I mean, the more weight that you have, the more energy it takes to get out of the Earth's gravity to launch it into space. And then the ideal date, as I mentioned, it basically, if you send it off at the right time, you'll use less fuel for a Mars trajectory. But again, the propulsion system is a major challenge right now, and the launch window determined by payload and velocity. We're looking at different things, nuclear propulsion. We're looking at plasma propulsion, different ways of trying to get astronauts safely to Mars and beyond. I mean, Mars right now is very far away. Here's the thing that just boggles my memory, my mind, is how big space is. I mean, we live in a solar system with roughly 9 planets. Pluto comes in and out once in a while. But if you think about the Voyager 1 spacecraft that was launched in 1977, it took it over 40 years just to get outside of the solar system. And it was going about 35,000 miles per hour. And so, just getting out of our solar system with technology as we have it, it still takes a very long time. And imagine going from one solar system to another solar system in our galaxy. We're talking maybe hundreds of years. And so we got to have propulsion systems, kind of like Star Trek, that can take us to warp factor 5 or warp factor 10 to get to another planet or another solar system very quickly. And then let's talk about entry, descent, and landing. All right, so landing on Mars. I show a picture here of a spacecraft going to the Martian's atmosphere, but the Martian atmosphere is very thin, and so it's very difficult to land very large payloads, very heavy objects. Like for example, a habitat. Okay. These are very large and very heavy at this point in time anyway. In talking to some friends of mine at Jet Propulsion Laboratory regarding the Mars Science Laboratory Curiosity robot that weighed about 2,000 pounds, if you saw pictures of how it landed on Mars, that was the maximum weight that can be landed safely on Mars using that method. Anything bigger than that is going to be very, very difficult just because of the nature of this large objects, these large mass. Well, if you got large mass, you're going at a certain speed. What is that? Kinetic energy, right? 1/2 mass times velocity squared. And so how do you bleed off that kinetic energy to land safely on Mars? We're looking at, this is Glenn Research Center, looking at some what we call foldable large entry shields that can be folded into a spacecraft that fits very nice in the spacecraft, but can be basically unfolded to create a very large heat shield for very large objects, like, for example, habitats. And let's talk about reliable life support systems. Here's a simplistic view of a life support system that basically takes human urine and creates water, so they can drink and, shower and things of that sort. You have oxygen generation for generating oxygen and getting rid of the carbon dioxide that can pose problems, but you recycle that, for water. And then you have trace contaminant control as well. So these can be very complicated. In fact, you're seeing a picture here of the one for Space Station. That's the prototype system on the ground at the Johnson Space Center. And it's a huge system that requires a lot of technology, but we haven't been able to get it down to a smaller size just by the nature of everything that's involved in it. And then not only the one for a habitat, but also for what you're seeing here is a picture of one for extra vehicle activities. Very challenging. And a lot of things to overcome, and one of the most important is making a reliable system that will provide confidence, if you will, for the astronauts, that they're always going to have air to breathe. Imagine living in a place that you don't know if you're going to lose your air or oxygen one day. That's something you have to be aware of. And then uninterrupted power. You got to have power to power all these systems. And so, they're looking at nuclear type reactors. Right here at the bottom is a prototype that's being developed. I think it's at the Langley Research Center in Virginia. And this thing generates about 5 kilowatts. Well, we're going to need about 40 kilowatts at a minimum for habitat on Mars. And so we're going to need a few of these for providing power to just a very small crew of 4 astronauts on Mars. And in situ resource utilization, boy, that's a big word, but basically it's the way of using the land for creating water, for creating fuel, and maybe also creating dirt that's not toxic, like Mars soil is kind of toxic, and so the astronauts can grow food. Right now, the Mars 2020 that's getting ready to launch soon is carrying a very small in-situ resource utilization. This little box is called the Mars Oxygen In-Situ Resource Utilization Experiment, or otherwise known as MOXIE. It's a small unit, and it's about the size of a car battery. And this collects carbon dioxide from the Martian atmosphere and electrochemically split in the carbon dioxide molecules into oxygen and carbon monoxide molecules. And then the oxygen is then analyzed for purity, of how pure it is before being vented back out into the Martian atmosphere. So here's an opportunity that we're going to take advantage of to see if we can produce oxygen from the Mars atmosphere. And then communications, that's a big one too. From Mars to Earth, it takes about 20 minutes with some of the technology we have right now. We're looking at laser communications, like we can increase the communications by 10x, 10 times the amount of transmission of information. This is important because we need an opportunity or technology for astronauts to talk to their loved ones on Earth, and also sending data about the systems on Mars and seeing how well they're behaving. And so that way the models and simulators on Earth can perhaps update the information from the Mars systems in case something goes bad. Think about what happened on Apollo 13 is that, the systems were failing on Apollo 13, but they had a replica, somewhat of a replica on Earth. They were able to replicate the problem and figure out ways to save battery life and things of that sort. So communications, a biggie also as well, but there's some challenges transmitting data from a laser beam from Earth to Mars. You got the atmosphere that deforms the beam and things of that sort. So again, another one of those technologies that are going to be critical. And then the radiation effects, as I mentioned, the radiation effects are all, there's solar energy particles, galactic cosmic rays. Of course, on Earth, we're very fortunate that we have the Earth's magnetic field that basically provides a shield around the Earth to protect us against that. But that's not going to be the case on Mars. As you're going into Mars, you're getting away from the Earth's magnetic field. You're going to be going through the Van Allen belt, the lower belt and the inner belt and outer belt of the Van Allen belt that has a lot of radiation there. And then once we get on Mars, there's also a lot of radiation there, and that affects the body. You have the galactic cosmic rays is basically a slow varying cosmic ray considered like background noise, but it can change the DNA of your body. And then you have the high energy solar particle events that can happen at any time, being basically spewed out from the sun. And then the areas that can be affected are the lungs, the stomach, the colon, bone marrow, and reproductive organs. And so if we're going to be a civilization that we're going to perhaps have babies on other worlds, we need to protect against that. So how do we do that? Computer systems, they also suffer from radiation effects. Here there's a ground computer system. This is something representative of like Siri that provides speech recognition in the United States. And it's a huge room of these servers. I mean, these are just hundreds and hundreds of computer systems that basically do computation, artificial intelligence communication, computations. Unfortunately, because the Earth's radiation effects of space that can affect electronics, electronics are not as fast for space applications as they are on the ground. And so these are very costly, very expensive. This is, I think this is a RAD 750 radiation hardened computer processing system that costs about $250,000. And so our servers in space are going to be very small. And so we're going to have to be very efficient about developing systems that basically provide the, well, what I called earlier in my presentation, a onboard mission control system in a very compact, efficient weather. So we're going to have to try to figure out ways of doing a lot of computations in an environment that does not allow for using commercial systems easily in the deep space environment. And then maintaining the astronaut's health. This is something that's being developed on space station for collecting saliva, air, and blood to analyze the health of the astronauts. This is the first X-ray machine on board space station that's being tested. But keep in mind, that's on board space station. This may not work in the deep space environment because of the radiation effects. Again, the space station is protected for a large extent by the Earth's magnetic field. And then what we're calling telemedicine and teleoperations. You know, astronauts get sick on space. What's going to happen? We're going to have a doctor on Earth communicating with the people on Mars for perhaps performing an appendicitis attack. And of course, the big one is being near loved ones. And we can't do that, but we have something like telepresence. Maybe that will keep the astronauts' sanity in place. And then there's a lot of risk. You know, this is just kind of a representation of all the risks associated with developing systems, requirements, design, safety, testing, maintenance, and crew. These are barriers. These are all barriers that are in place to try to prevent an error happening. But because they're not completely developed, that there are holes in each barrier that perhaps represent deficiencies, a deficiency in the design, a deficiency in safety, deficiency in testing. Maybe we didn't test enough. And so there's a possibility that he's at the right time and cause an accident. And that's part of systems engineering, which is a biggie at NASA, is to try to close these holes as much as possible and avoid an accident, excuse me. And each barrier is spinning, which represents a deficiency happening in a certain period of time. And so in conclusion, the path to future space missions, you know, we're going to develop the technology to learn, to live and learn and work on other worlds, in this case, the moon, and then settle Mars one day. And then from there, on to other worlds. All right. And that concludes my presentation.
Yeah,
and
so thank you.
I think I'll return. I'll stop sharing. And
Yeah.
okay.
Yeah, so thank you very much, George, sir, for such a wonderful, the session, especially the technical challenges of human space flight. So it's a really wonderful thing, and we came to know about a lot of things during this session. So, Dr. Paramjit Singh, do you have any specific question for George Salazar, sir?
Yeah, I have. Thank you, Mr. George. Really, it was a very wonderful session, very enlightening. And I hope that all those who are watching, especially from the school and the college, they will be inspired to be astronaut and in the space science. So my first question for you is, what difference you see in the coming future in human space flight after SpaceX Dragon crew launch?
I'm sorry, could you repeat that, please?
Yeah. What difference you see in the coming future in human space flight after SpaceX Dragon crew launch?
Okay, so after the future, I'd see in commercial spaceflight, especially for Dragon and the success of it, is more commercial participation in the Artemis program. There's several commercial companies that are bidding for opportunities to provide certain services on the moon. So I think SpaceX and obviously some of these other commercial companies are now setting the stage for a new paradigm in space operations, where you're seeing commercial companies that their commercial companies are in the business of making money and satisfying the stockholders. And so they look for very efficient, effective ways of developing systems, for space applications. So I kind of see new things being invented by the commercial sector that maybe is more cost effective than if the government was to invent it.
Okay, sir. So yeah, so thank you for the answer, sir. So I have one more question from a student. He want to know when we are going to have an electronic propulsion system in our rockets or spaceships.
Electronic propulsion systems?
Yeah.
Okay. Yeah. It's a good question. So, right now, we've developed some ion propulsion thrusters that were used for small spacecrafts, and of course, they can't push very large, massive spaceships like they're going to be required for human spaceflight. But we are looking at the nuclear propulsion type systems that can do that. And we're hoping that by the end of this decade, that we'll have at least a good working prototype of a nuclear power type system. Very challenging, very political, because the whole thing about nuclear power going up into space is sometimes scary for some people, and so you have to get. It's not so much the technology as much as it is dealing with the politics of sending nuclear power into space.
Okay, so that's really great. So I have another question from Pranav Chaudhary. So he want to know how robotics or humanoids play an important role in human spaceflight.
Robotic systems in human spaceflight?
Yeah.
So, as I mentioned, it's very dangerous for humans to go and do extra vehicle activities. And so if we can get robots, to do a lot of the work for astronauts, that reduces the likelihood of an astronaut getting more exposure to radiation as well as hazards. Now, robotic systems, if designed properly, they have all the capabilities. They can do wonderful scouting. I mean, think about the Mars Science Laboratory, that Curiosity that has all the capabilities on board. So we send these, let's call them scouts, out to the different parts of Mars and the Moon. Then we'll be able to gather more information more quickly and more safely. And so the proving ground for that, again, is on the Moon, where astronauts maybe can send out a swarm of robotic systems and control them centrally inside the habitat, and they can gather much more information as just one or two astronauts going out by themselves.
Yeah, definitely, sir. So I have, sir, one more question from Nirban. He want to know space debris is harming space environment or not?
Say that again, please.
Space debris or space junk is harming space environment or not?
Space junk. Oh my gosh, there's just so much out there. I tell you what, if somebody can come up with a good, let's call it garbage collector for space junk, they're going to become very rich. There's just so much space junk out there, and it's making it harder and harder to basically do space operations. I can't tell you how many times space station has to dodge orbital debris. Shuttle got hit many times by orbital debris. In fact, the first hit of the space shuttle happened on the second flight of the space shuttle, and it cracked the window, the front windshield of the space shuttle, and it was probably about a 4-inch crack. And keep in mind, this glass is about 3 inches thick, and it cracked it. And you know what cracked it? It was a paint flake. But you say paint flake, that's not big at all. Well, if it's going 17,500 miles an hour, that's a lot of energy.
Definitely. Yeah.
Mr. George, I have one question for you.
Sure.
Uh, what advice or tips you will give to the students from your 30 years plus experience so that they will be as successful in this field, space field?
What advice can I give to them?
Yeah, out of your
For,
30
for
years big experience, extensive and intensive experience, so they will be benefited in real time.
I mean, from my experience for students is obviously, study as much as you can, all your, science, technology, engineering, mathematics. But I also, and maybe this is obviously something that you all are probably doing at your schools, is providing opportunities for students to work in teams. Teamwork is very, very important at NASA, and we got a lot of people that are very smart, but they say two brains are better than one, and so learning to work in teams is very important. I'm involved with something called Texas Space Grant Design Challenge, where I give challenges to universities here in Texas in the United States, and so it's an opportunity for them to learn about problem solving. Okay, take the problem and use. I sometimes I tell students about the engineering method and the scientific method are very similar. It's a very methodical way of defining the problem, looking for a possible solution, form an experiment, do the experiment, look at the data, and compare it against your hypothesis. And if it's not working, you start changing it. But it's an opportunity to get people to be thinking about solving problems. Book problems are good and all that. Kind of teach them stuff like that. But the real learning happens when you're tackling real problems. And so and what I learned is it's just not the problem. Sometimes you have to deal with. You have to deal with personality, interactions of personalities. That's teamwork. I've worked on teams where I had very smart engineers, but very hard to work with. And so you have to, what I call learning the soft skills, communication skills, negotiation skills, all of the communication skills, both oral and written, dealing with problem solving. So these are your soft skills that in engineering school are ordinarily not taught. They teach you a whole bunch of technical stuff, but very little about the human element. But what I have found out over the years is sometimes it's equal or sometimes even more important to learn working with humans, working with people.
One last question. So many times, many students, they ask us as a teacher, as a principal, what suggestion you will give to parent as well, teacher, so that they motivate or give that kind of environment to the students so that they develop the scientific aptitude.
For teachers?
Teachers as well as parents, so that they can create that kind of environment that every child must develop scientific and aptitude.
Yeah. That sometimes it's a challenge. I know here in the United States, some schools don't have the money, the funding, for doing some of that, for creating laboratories, but sometimes. I was working with a school on the poor side of town in Houston, and what we did was we did kitchen science, okay? And I call it kitchen science because things like, for example, taking a hard-boiled egg and putting it inside an egg and lighting a fire inside maybe a baby bottle and basically creating a zero vacuum and let the egg being sucked into the bottle. Paper airplanes, doing competition. Who can design the best paper airplane that goes the furthest? Who can, let's say, for example, a balloon. Okay, how can we protect the balloon from being popped when we put a needle through it? Okay, and get them thinking about that, or give them a bunch of little toothpicks and say, I want you to build a bridge that can hold 10 pounds of weight. Okay. Very simple, very cheap, and so sometimes it's not so much the money, but the activity. I'm reminded of my granddaughter that my daughter and her husband buy her expensive toys, but sometimes all she wants is a little stick to play with and learn how to play with the stick, so sometimes you don't have to have a lot of money to, to create that environment, but it's important for the parents to work with the, the kids are learning at school, but also the parents help that out, to reinforce a lot of that learning.
Thank you very much, George. It's a really very right answers and the appropriate answer for the teacher. Those who are listening, they must be benefited. Thank you. Over to you, Saurabh.
Yeah, so sir, let me take my last one or two question because of the time limitation. So sir, I have received this question from fifth standard student Sudhvit Tagore. He want to know, sir, how can I join NASA as an astrophysicist and what studies do I need to pursue? He's in fifth standard and he want to join NASA as an astrophysicist.
All right, so here's the thing. It's challenging. Joining NASA. So when I hear the word NASA, so we got NASA government, and that's what I belong to, NASA civil servant government. But there's also NASA contractors, and like Lockheed Martin, Boeing, and some of these other ones, and then there's a private now, SpaceX and Blue Origins, all these. So in the United States, anyway, you usually have to be a U.S. citizen. Astrophysics, usually there's a couple of centers, not NASA centers that deal in astrophysics. One is Glenn Research Center, Goddard Spaceflight Center, and also to some extent Jet Propulsion Laboratory as well. But the thing is that I'm going to use an example of a young lady that's from Delhi in India, and many years ago she asked me, I want to join NASA. And I said, at that time, I said, it's a long road. And I was telling her, she said, I don't care. I want to do it. And so, I communicated with her. And so she got a bachelor's degree in India. And then she transferred over to Syracuse University in New York City and got her master's in computer science, because I told her AI and machine learning is really big in NASA. So she graduated there. And now she's in California pursuing a PhD, and she's looking right now for a professor that's working with NASA in research in artificial intelligence. So she started out as an undergraduate in India, and now she's getting very close to one day working at NASA. So it's a long road. It's not that it's not possible. It just takes patience.
Definitely. Yeah. So sir, my last question. I have received a question from teacher Suman Verma. She want to know how does a long space flight affect someone's mental health?
So long space flight, mental health. So that's the one that's rather challenging. And let me give you an example of that. Many years ago, I attended a conference at the Johnson Space Center, and there were some Russian scientists that came in, and they were talking about some of the long duration studies in Siberia, that they do isolation studies and stuff like that. And I had an opportunity to talk to one of the research scientists, and so he was telling me that he's done a lot of those research studies, and so I get varying results. But he said one time there was this one crew that told him this was off the record, that don't record this, but he said the reason that they lasted so long in isolation is because they knew that they were on Earth, and that one day that door was going to open and they were going to get out and they were going to see their family. Not so when you go to Mars. Mars is far away, and so we still don't know how that's going to affect them. And so here's the thing about affecting you psychologically, is that if you're depressed, if you're not feeling well because you miss your family, your attention to controlling systems can be bad. All right, and that's why human error, we study that very well. I just mentioned earlier to the principle about the human errors and associated with controlling systems. We have to be aware that the human element is not predictable. You can design hardware systems that you can predict how they're going to behave. You can design it to behave a certain fashion. You can write software for the most part that's supposed to behave in a certain fashion, but humans, it's very hard to predict the behavior of what's going to happen. Physiologically, psychologically, interaction with the people, the teams. I don't like that person. I'm not feeling well. I'm depressed because I haven't seen my daughter in a year and a half. And so now I'm going to take control of a system, and I'm in that mood, So, it's not just the challenge of dealing with being depressed and being isolated and lonely, but it's also the challenge of developing systems that can basically detect that and avoid a bad decision.
Exactly. So thank you very much, sir, for such a wonderful session and giving the answers of all the questions, the queries which students have asked due to some time limitations. So we have to conclude this session. So I request Dr. Paramjit Singh to please conclude this session with a word of thanks.
Thank you, Saurabh. Thank you, Mr. George. Really, it is my pleasure that I am part of this webinar today. And the session you have shared with us, the time you have given to us, I am definitely sure that students, those who are watching you live on YouTube and the Facebook of the Smart Circuit, they will be definitely benefited and they will be inspired to enter in this field. And no words that how beautifully and nicely you have explained this your presentation, and I'm hopeful that in the future also we are going to listen from you, and we are going to be enlightened by your very productive and enlightened session. Thank you very much, Mr. George. Thank you very much, and thank you, Saurabh, to
Thank you
giving
very
me
much.
opportunity to become a part of this great session.
Thank you.
Thank you.
Thank you very much, George Salazar, sir. Thank you very much, sir.
Thank you. My pleasure. Thanks for
And
having
Mr.
me.
George, from my side, whenever you will be in India, you will be my guest.
Oh, well, thank you very much. I appreciate that.
Pleasure will be mine.
All right, sir. Thank you very much. Thank you very
Thank
much,
you.
sir.
Thank you.
Yeah.
Jai
Thank you.
Hind.
Bye. Jai Hind, sir.
Bye-bye.